So this is where some people got the idea that maybe there is a better way. And I wanted to point out that this is only the tip of the iceberg of what we'll call better ways of having better instruction sequences or better encoding standards between compilers and the hardware. This is actually an open sort of research topic now. Very long instruction word processors, or VLIW for short, is one take on it. There's been a fair amount of work done after this, which we're not going to be talking about in this class, sort of in the last 5 to 10 years, that has looked at this in a little bit more detail, especially given sort of multi-cores and can you schedule across multiple cores. Or there was a project out of University of Texas in Austin, which tried to schedule across something that sort of looked like cores, but wasn't quite cores. That was sort of, we'll call a super VLIW, but had some dynamic aspects and some static aspects. But for right now, let's talk about very long instruction word processors. Okay, where does the name come from? Let's start there. Well, these things were actually originally called long instruction word processors. The name kind of fell out of favor. At one point, people made a differentiation between long instruction word processors and very long instruction word processors. And it was kind of on how many instructions were packed together. The differentiation is largely sort of fallen out of favor now, and people mostly call all of these things VLIWs, or very long instruction words, because it's hard to say what is long, what is very. It's kind of just an extra term. It's kind of like people talking about large-scale integration versus very large-scale integration versus ultra-large-scale integration, or people just sort of keep tacking on extra letters in the front. But let's talk about VLIW instruction sequences and what does one of these things look like? Well, a VLIW instruction will actually have multiple operations within one bundle. So typically, this is either called a bundle or an instruction, with multiple operations inside of it. So in this example here, we have 6 operations that can be executed in this one instruction or in this one bundle. And typically, there is sort of fixed format. So let's say you can execute 2 integer operations, 2 memory operations, and 2 floating point operations per cycle, and that's what you're allowed to encode. So instead of having on the disk a sequential sequence of instructions, now we still have a sequential sequence of instructions or a sequential sequence of bundles, but each one of those instructions, each one of those bundles will actually encode multiple independent operations. So let's look at sort of an example code sequence of this. So for instance, you could have something that looks like this. Let's say so what's interesting about this is we can see that there's actually 2 operations in this first instruction, in this first bundle. The second one only has 1 operation. And this multiply and this add will actually execute, semantically at least, they can execute in parallel. Now, what's interesting is if you look at this, I purposely wrote this to show what looks to be a read after write or write after read or some sort of dependence between these two registers and these two instructions here, this mul and this add. But that's not what's actually going on here. In a Verilog instruction word processor, within one instruction, within one bundle, these sorts of dependencies are ignored. So just because this reads R3 and this writes R3, they're not dependent on each other. The subsequent instruction is dependent on R3. Let's say if this was R3, then that would probably read the result there. But within one bundle, it doesn't actually matter. So the semantics of the instruction set are everything within one instruction or everything within one bundle are parallel with each other. And there's not dependency checking. What's nice about this is we just took all that piece of hardware that we built. We took all that instruction checking, all the dependency checking, all the scoreboarding, and we just threw it out the window. We don't need that hardware anymore in this instruction set or in this architecture. So that's pretty cool. So we actually took out a bunch of hardware that we didn't need, and we basically let the compiler do that checking for us. Now there's a question of this mul. If this multiply takes multiple cycles, whether this instruction here picks up the result of R3. Sorry, should be drawn the other way. Or let's say if the add had longer latency, if it doesn't pick that up. And we'll talk about that in a minute. There's sort of two different choices there in VLIW designs. Well, let's look at our slide here. Typically, in sort of traditional VLIWs, each operation has a certain amount of latency. So, and it's guaranteed. Unfortunately, because of this, the architecture of the machine is very tied to the compiler. The compiler needs to know how long each operation takes. So that's sort of a downside. And in a typical VLIW, there's no data interlocks. So we don't even have a scoreboard. Now, there are some architectures which do enforce interlocking that are VLIWs. But in sort of the traditional, most basic VLIW, you don't have a scoreboard. You have no interlocking. So if you were to have, let's say, this subtract operation were to read register 1, which the mul wrote. And the mul, let's say it's a floating point mul. It took four cycles. In the most basic operation, this mul here would actually get the old value of R1. So it would not get this value. Instead, it would get the original value of R1. But we'll talk about that in more detail in a second. There's a sort of a choice there in VLIW designs. But yes, so we reduced our hardware. We don't have a registry namer. We don't have an issue window. We don't have a reorder buffer. We don't have a scoreboard. And we let the compiler do a lot of the work. Downsides to this. We're not able to react to dynamicism very well, or dynamic problems. So cache misses, branch mispredicts, things like that. Because we're not going out of order, because we don't have all that extra hardware in there, we can't go schedule around those problems. So that's a downside to these architectures. Now, people have thought really hard about how to make VLIWs have some of the benefits of superscalars and out-of-orderness and out-of-order superscalars. So at the end of lecture today, and probably in the next lecture, we'll talk about some of the techniques that people have added back into VLIWs that bring us somewhere in between an out-of-order processor and a VLIW processor and get some of the benefits of both. OK, so two models. This goes back to when you have an instruction which writes to a register, and the latency of that instruction is coded to be longer than 1, which value do you pick up? Do you pick up the old value, or do you pick up the new value if you have an instruction which is effectively in the the shadow of the other instruction. So the first VLIW model, and this is a sort of classical naming scheme. I did not come up with this. It's called the equals scheduling model. So the equals scheduling model, you have a instruction, and the latency of the instruction is specified. The compiler knows it. And if you have an instruction which tries to read a value that gets written to before the first instruction actually does the write, it'll get the old value. So let's go through an example over here. So we're going to have our multiply again. OK, so here we have a mul and an add, which are bundled together. So they're going to execute concurrently. We have an and instruction, or and operation in the second instruction, in the second bundle here. I should say that I'm using brackets and semicolons to delineate sub-operations. Or the brackets delineate an entire instruction or entire bundle. The semicolon is just there to delineate between two operations within one instruction. And here we have an and. We have what looks to be a read after write dependence here. Something like that. And let's say our pipeline looks like this. We have x0, which does ALU ops. We have y0, y1, y2, y3, and then we have, let's say, a two-stage memory pipeline. And somewhere over here, we have sort of write back. So this looks similar to sort of pipes we've looked at before. But now comes the question, let's say multiplies go down this four-stage pipe, very similar to things we've looked at before. Loads and stores go into the memory pipe, and ALU operations go into the X pipe. Should this AND get the result in the multiply if it's scheduled one cycle after it, or should it get the old value of R1, the previous value of R1? So we're going to define in the equals scheduling model that the multiply value for R1 is not ready until the end of Y3. So in the equals model, this AND, the compiler is not trying to express a read after write dependence. This does not actually exist. It gets the old value of R1. And the compiler knew about this, and everyone's OK with this. Now, if this AND was, let's say, 3 more cycles later, it would actually get that value, and there would be a read after write dependence. So in the equals model, we're just saying that the operation takes effect exactly at the specified latency and never earlier. Some positives to this is you get some pretty cool register usage. So if you think about it here, register 1 was live after this multiply. So effectively, this gives us a little bit less register pressure. We can have a little bit more registers in flight without having more physical registers or having more architectural registers at all. We can basically just have more registers because it doesn't go dead when we overwrite it. It goes dead when this multiply takes effect. So as I said, we don't need any register renaming. But the compiler really depends on not having the registers visible early. Unfortunately, this causes some problems, these sorts of architectures. This is actually the sort of first formulation of very long instruction word processors looked like this. There's these equals architectures. The major problem with these actually comes around if you have things that are unpredictable mixed in with this very predictable code sequence. So let's say you take an interrupt. Let's say we just put some unimportant instruction here, some subtract operation. The subtract takes an interrupt. Now, semantically, this multiplication and this add complete because the interrupt doesn't happen until the instruction after it. It doesn't happen until this subtract operation. OK. Now you fall into the interrupt handler for the subtract. What happens when the AND goes to execute? Does it actually pick up the correct value of R1 here? No. It picks up the new value of R1, and it was supposed to pick up the old value of R1. So that's traditionally a problem with EQ or equals scheduling model architectures. People have solved some of these problems. Or sometimes when people build these processors, they don't have interrupts. So some of these VLIW equals processors were not able to handle interrupts at all. So that's something to think about. That's sort of the first case. Now let's look at a little bit more forgiving case. We'll call it the less than or equals model, or LEQ scheduling model. So here in this model, a value is allowed to become value. A register value becomes valid with the new register value anytime between when it issues and the scheduling latency. So what this means is the compiler still can't schedule an instruction early. So it can't go and try to read the value early, but you're guaranteed not to have a problem when there's an interrupt if, let's say, you come back and you filled in the right value. So the compiler sort of schedules around this and knows not to schedule something too early. So you still don't have to implement interlocks. You still don't need a scoreboard. But you can now have precise interrupts. Some other positive things pop out of this. You end up with binary compatibility preserved when the latencies are reduced. So let's say you make a faster processor where your multiply, instead of taking 4 cycles, only takes 3. That's a positive here. You may not get more performance from it, but at least you won't get incorrect execution. So that's a sort of a positive outcome here. OK, so a little bit of history. Usually I try to not harp on history too much in this course, even though I really enjoy it. The VLIW processors is. I wanted to make one point that a lot of this research is relatively recent. So if we go look at sort of the dates on this, these first processors and the first real VLIW processors was done in like the late 80s. So this is not going back to the 60s. This is like a portion of computer architecture work which is actually very, very recent. The first long instruction word processor was actually a floating point systems, FPS, that's what it stands for, processor. And this was actually a coprocessor to VAX machines. So it's something that could speed up your floating point on a VAX machine. This was very much the most basic VLIW processor. There was no interlocking, didn't take interrupts. It was really sort of for hand-coded vector arithmetic and floating point math. Probably when people talk about VLIW, the thing that pops into their head first is actually the multi-flow trace processor, which was made by a small startup company called Multiflow. This was an outgrowth, actually, of a bunch of research that was done at Yale by Josh Fisher and a bunch of his students. And I won't go into too much detail here, but one of the interesting things is they really, really did have a long, very long instruction word here. 1,024 bits long instructions. So this is like a beefy instruction. This is, and you can have anywhere from 7, 14, or 28 operations per instruction. And this was not dynamic. What this actually was is this is how they made different configurations of their machine. So they actually had wider machines that were more expensive and narrower machines that were cheaper. So sort of a family of processors, and they customized the compiler to this. Josh Fisher actually is much more of a compiler guy probably than an architect by training, and you can sort of see that in his group's work and the PhDs that have come out of it. He now works for HP Labs, and is sort of semi-retired. At the same time, actually, there was also another company that was commercializing a very, very similar idea. This was the Sidra 5. This was Bob Rao, who's another very famous computer architect. He was a professor at the University of Illinois, and he developed a lot of these things, then sort of left and started Sidrome. And some of the interesting things in that processor is they had this cool thing. Instead of having a register renamer, they had a register file that the naming of the registers sort of changed as you did sort of function calls. We'll talk more about that later today, or maybe tomorrow, or maybe next lecture. But more really want to get out here is this is very recent.